Good morning, kids. We are going to discuss the current electricity one shot. The one very fundamental chapter, very important for JEE mains and JEE advanced. For JEE mains, two questions compulsory in every shift, two questions, and for advanced, two questions and mixed concept. So this particular chapter again is interlinked with RC circuit, electromagnetic induction, alternating current, photoelectric effect. Everywhere the resistance ideas will be using it. So therefore, it's a show compulsory chapter which everyone should learn, revise, and you should solve PYQs of this concerned chapter. So watch all the particular things, what all I'm explaining within one and a half hour, this particular current density ideas. Learn it, not only mere watching, learn it. Then read again, remember all the formulas, then solve PYQ, you can see the benefit in exam. Okay, what should be the strategy for current density? How we should prepare this current density? So the topics which you should going to come across current density one shot. The first is the basic Ohm's law. What is the Ohm's law? What do you mean by electrical resistance? And what is the Ohm's law? These ideas is what you are going to learn in the Ohm's law here. Then afterwards, the power dissipated regarding the energy supplied by the cell, power dissipated in the bulb, in the resistor, in the electric kettle, those ideas will generate and some formulas. Then we'll introduce the idea of the cell and battery, which will supply energy to the circuit. Then we'll discuss the resistors series parallel, very important one. Then KCL, Kirchhoff's current law, Kirchhoff's voltage law, loop method, nodal analysis. These are all the circuit finding unknown things, all circuit methods they are called as. Then we'll come back to the cell concept, internal resistance of a cell and grouping of cells. These things will cover here. Then bulbs in series parallel, which bulb will have more brightness, these things. Then Wheatstone network, this is a small application. Then finding equivalent resistance of different shaped circuits. When plenty of resistors are there, how to find out. Then conversion of galvanometer into ammeter and voltmeter, meter bridge, potentiometer, post office box. One more, temperature coefficient of resistance. Vary temperature coefficient of resistance. So all these things we are going to learn. So you should gather all these topics and each and every topic, listen first carefully what sir is teaching, understand the concepts, all the formulas which you come across, make a list of that one, remember it daily, go through it, solve PYQ. Definitely you can do very good in JEE mains, and also the same strategy for advanced. Okay, we'll start now. Okay, kids, first, like, what is electrical resistance? It's opposition offered to the flow of charge by the material of by the material of a conductor. So what is a conductor? Conductor basically contains free electrons which will move randomly with a very high speed. I'll connect a cell. Because of this cell, there will be a potential difference set up, here plus minus. Because of this, electrostatic field is generated inside the conductor, and because of this, the electrons will experience a net force towards right. Then it will also have the random speed. The resultant of this, it will be moving zigzag path. Why do they zigzag path? Due to collisions. So in fact, this electron will encounter collisions inside the conductor. Due to that, this zigzag path will be there. Then it's going to drift. So this speed is given by. So once again, I'll revise it. The cell, it will generate a potential difference. Then because of potential difference, E bar is set up here. This E bar electrostatic field vector will exert a force on the electron, and this electron will experience a force. Due to this force, it will start drifting. Then it will move from left hand to right hand gradually with a speed called as a drift speed. This drift speed will define using this particular formula. Okay, fine. So the drift speed depends on what? The charge of electron, mass of electron, relaxation time tau, and the applied electric field inside the conductor. Okay, then we'll define the current density. So what is J? J is called like a current density. Here only I'll write it here. And how we define this is like a concentration of electrons, charge of electron into this speed. So what is eta? Eta will define it here. Density of free electrons. Okay, fine. So this relaxation time depends on these quantities. Then further simplifying, we'll get the Ohm's law. The current density will be related to the conductivity of the material and the electric field. So where further the conductivity and resistivity will be inversely proportional, J equal to E by rho, we'll write it. Current density, how you define current per unit is vector quantity. Where the electric field should be potential by length, or the potential applied V, E, and what is the length of the rod is L. Length of the rod is how much here? It is L. The total length of the rod, it is L. In what direction the current? Current is flowing in this direction. So we'll define the electric field strength as E by applied EMF by length. Solving this, we'll get as rho L by A. This E by I is what we'll call resistance. This R. No, sir, what do you mean by resistance? And you are telling some voltage potential difference we applied here. Then we have the electric current. This one. So how all they are related? Like the potential difference will make this charge to pass through it, whereas the resistance, what happen, will by like this particular, you can say like a loop is there, so we can control the diameter of the loop, the nose, what you can call it. So based on that, what happen, this particular charge, what happen, this current will experience some sort of opposition due to this resistance. No? So this particular thing, we'll write it here. This is called like a ohm resistance. This particular thing is current. And this is the potential difference. Okay, fine. So when we apply the potential difference across the cell, the potential difference across the cell will push the charge. Then the material will offer resistance to the flow of charge. And that's what the resistance. So therefore, will it block the flow of charge? No, it will oppose it. So it will just control the flow of charge, this resistance. So that's what we'll call the electrical resistance. The electrical resistance depends on what length and area of cross section. What is the length here? Length is this one. What about area of cross section is this one. Or in this diagram, this is the area of cross section. And this part is what? The length. And the material, rho is the material. So the electrical resistance depends on the resistivity, length and area of cross section. There's one basic formula which you have to remember. The unit for this will be ohm. And this is a basic Ohm's law. Okay, what actually happens in terms of energy? This particular cell will supply energy. The positive charge will flow like this. It will encounter collisions, and due to that inelastic collisions, it will lose its kinetic energy and heat will be generated. Once energy becomes zero, again it will return back to the negative terminal. Again the cell open will energize the charge, again the charge will move. Actually there is no positive charge. Hypothetical we are assuming. Actually who will flow? The electron only here. We are for our convenient, we are assuming hypothetical positive charge. The direction of flow of hypothetical positive charge will call it as conventional current. Actually who is flowing? Electron is flowing. Opposite to flow of electron, we are assuming an imaginary positive charge. So therefore this is called like a conventional current. Okay, what is actually the basic concept? The cell will energize the charge. So the energetic charge will pass through this wire will enter here. Here it will utilize that kinetic energy to overcome the resistance. And here when it is moving, it will encounter inelastic collisions. It will lose its kinetic energy in the form of heat. Then once energy becomes zero, will be attracted by negative terminal. Like that, the charge will circulate through this particular closed path. The cell will give energy. The conductor will convert that kinetic energy into the heat energy, and again the charge will come back here. Like that, continuously there will be flow of charge. Continuously there will be supply of energy by the cell to the conductor. Who is involved in the transfer of this? The charge, the electron, or the conventional positive charge. This is a basic idea. Okay, now if you look at this, there's a cell. So what it does, it will supply the energy, converts chemical energy into electrical energy, and the current will flow, the charge will flow like this. Fine. Now this energetic charge, when it encounters here inside the bulb, the kinetic energy will be converted into the thermal energy due to the inelastic collision between adjacent atoms and the material. Then that heat will be converted into electromagnetic radiation, and the bulb starts emitting light. This is one basic principle here. Then again this charge will continue its path. So what this bulb converts? Electrical to heat and then to light. This is a conversion occurs. So here we'll show that one. The positive charge will leave here, energetic positive charge. It will enter here. Then as we know, positive charge will move from higher to lower potential. Here it will encounter inelastic collisions, heat will be generated. Or thermal power generated. And this supplies energy. And the same charge will continue to flow like this. Charge of a cell should be conserved. Huh? Okay, no. Cell will energize the charge. The energetic charge will pass through this resistor, will encounter inelastic collision. Nothing but that will call resistance. More number of collisions, more resistance. Then once then it will return back and will enter negative charge. Again the cell what pen will re-energize it. Again the charge will go through it. So what is actually happening? Who is transferring energy? This particular electron, or nothing but the hypothetical charge, which is carrying that energy from the cell to the resistor. What resistors will do? Will convert electrical energy into the thermal energy. So similar to this one, suppose that this skid is there. If this skid is on the ground, when the skid climbs up, then what energy will increase? What energy of the kid will increase? Its gravitational potential will increase. Then when the same kid starts sliding here, then the gravitational potential will be converted into kinetic energy. Then there will be friction will be there. Due to friction, heat will be generated, and finally again it will come to rest here. So look at what is the energy conversion, how that energy conversion is taking place. The kid Wattman is at rest, starts climbing up. Then its gravitational potential increase. Then is on the top. As it starts slides, potential energy converted into kinetic energy. The kinetic energy will be converted, will be utilized to overcome the friction. It will come to rest here. So what is energy conversion? The mechanical energy which is present in his body will be converted into increase in chemical energy which is present in his body, in his cells, will be converted into rise in gravitational potential energy. The gravitational potential energy converted into kinetic energy, and the kinetic energy is converted into heat by the friction, and it will come to rest. The same thing happens. The cell, what will happen? Will reaction will occur, chemical reaction will occur, energy will be generated, they'll be given to the charge. With that energy, the charge will proceed like this, and the charge will acquire that energy in the form of kinetic, and the charge will pass through with that kinetic energy through the resistor. It will utilize that energy to overcome the resistance of material by undergoing collisions. Once energy becomes zero, again it will enter negative terminal. Again the cell what happen, using its chemical reaction, it will convert chemical energy into kinetic energy of charge, and once the charge acquires kinetic energy, it will pass through the resistor. Here with that kinetic energy, it will encounter in elastic collisions, it will overcome the resistance and it will lose all its energy and again return back. Continuously the flow of charge will occur, or nothing but there will be flow of current. So according to the Ohm's law, we have the E equal to I R. E is nothing but V. V is what? The potential drop. E or V, both are same. Then what is the power dissipated? Power generated by cell. Let me write it here. E into I. This is the power generated by the cell. Then electric power dissipated in resistor R, which should be equal to I square R or E square R or E into I. And this much of electric power is dissipated in the resistor. The cell will convert chemical energy into electrical energy, and that electrical energy will be carried by the charge, and the charge what happen will convert that electrical, the charge what happen will, the resistor will convert that electrical to the thermal energy. This is how the energy conversion occurs. So the power dissipated and the power dissipated in resistor and the power generated by a cell, these are the formulas. Next topic, we have the resistors in series. What do you mean by series? Like two resistors, if the current flowing through them remains constant, then they are said to be in series. Then there will be a potential drop V1 and V2. So what is V1 is equal to? V1 equal to Ohm's law, V1 equal to IR1. What is the effective resistance of this circuit? I want to replace these two by an equivalent resistance, so that the same current I should flow. So what is V0? We'll write it as I into R. Then first we'll define like this: V1 plus V2 is equal to V0. What is V1? Ohm's law, IR1. V2 Ohm's law equals second resistor, IR2. V0 equal to IR. So what is R equal to? R1 plus R2. If two resistors are connected in series, the effective resistance will be R1 plus R2. Then the potential drop formula, IR1, which is equal to V0 by R, or V0 R1 by R1 plus R2, IR2. There is a potential difference. What about the power dissipated? Power dissipated should be equal to I square R1, I square R2. If R1 greater than R2, V1 greater than V2, P1 greater than P2. If two resistors are in series, the one which is having more resistance, the power dissipated will be more. The same thing concept applicable for the bulbs also, very, very important. We have the two resistors. With the current flowing through them, if it branches, the current flowing through them, if it branches, I2 I1. Here I'll indicate I2, I1. Then they are said to be parallel and there's a potential drop. What do you mean by parallel? The potential difference will remain common. If the potential difference remains common, then they are said to be in parallel. Then the effective resistance will define it as I equal to I1 plus I2. What is I is equal to? V naught by R. I1 equal to applying Ohm's law. V naught by R1. V naught by R2. So when two resistors are in parallel, effective resistance is 1 by R1 plus 1 by R2. Then the current I is equal to I1 equal to IR2 by R1 plus R2. Current divider formula. This is a current divider formula. Current in the first branch equal to main branch current into resistance of other branch sum of resistance. Similarly, current I2 is equal to IR1 by R1 plus R2. What about the power dissipated? P1 equal to V naught square by R1. P naught equal to V naught square by R2. R1 greater than R2. R1 greater than R2. Then the current I1 will be less than I2. P1 less than P2. The one which resistance, the resistor which is having more resistance, power dissipated across it will be less. There is a basic condition for the resistors in parallel. There is a current divider formula. So when two resistors are in parallel, the one which is having higher resistance, it will have less power dissipated. Next we have the Kirchhoff's current law. So it says that algebraic sum of current entering in junction should be equal to algebraic sum of currents leaving a junction. Suppose if this is the junction we have I1, the currents which are entering are I1, I2, currents that are leaving I3, I4, even I5 let it enter. And this is based on the conservation of charge principle. Then according to this, I1, I2 are entering. That should be equal to the one I1, I2 and I5 they are entering. That should be equal to I3 plus I4. Or this is equal to I1 plus I2 minus I3 minus I4 plus I5 equal to 0. Charge should be conserved. The algebraic sum of currents entering junction should be equal to algebraic sum of currents leaving a junction. Next we'll take the Kirchhoff's voltage law. So this is algebraic sum of EMFs is equal to algebraic sum of IR drops in a closed path or loop or mesh. This should be equal to like this. EMFs should be equal to algebraic sum of IR drops. This will explore it. Suppose if I have the circuit like this. Ohm, 4 ohm, 6 ohm, 4 volt. Then, what about the current flowing in the circuit? How to find out that one? So we'll assume the current, let it flow. in this direction, according to convention where current enters positive, where it leaves negative across the resistor, because current will flow from higher to lower potential. So based on that, the polarity. So current I then will traverse the loop. You can traverse clockwise or anti-clockwise. So I'll move from here. So just imagine yourself you're walking along the loop from here. Minus 2i plus 4, rise in EMF plus 4, minus 4i plus 6 minus 2 minus 6i equal to 0. So the I will be equal to total applied EMF will be 8 by 12 or 2 by 3 ampere. And you can find out even potential drop also. If you want to find out the potential difference VAB, you can use this method. VA, where you begin should be positive. VA minus 2i plus 4 minus 4i plus 6 minus VB 0. VAB is equal to 6i minus 10. 6 into 2 by 3 minus 10 minus 6 volt. So this shows that VA less than VB. Like that you can write the KVL. This is called like a loop equation. Kirchhoff's voltage law, the loop equation. How to find out the potential at point 2. So I have the circuit like this. These are potential V1. These ends are maintained at potential V1, V2, V3. We have to generate the we have to calculate the potential at point 2. Then we'll assume the flow of current. Let the current I1, here I3. Let this be I2. Or we can do like this. Then we'll apply KCL at point 2. What the current I1 is entering, I2 is entering, I3 is leaving. So according to the KCL, I1 and I2 they are entering and I3 is leaving, so negative. So there's a one equation, KCL. Then we'll write the how many unknowns are there, like a V0. V0 we have to find out. We'll apply the loop equation where the current is entering positive, where it leaves negative. Positive, negative, positive, negative. Now we write down the equation. V1, I'm starting from here. V1 minus I1 R1 minus I3 R3 minus V3 equal to 0. Similarly, V2 minus I2 R2 plus I1 R1 minus V1 0. Then V3 plus I3 R3 plus I2 R2 minus V2 equals 0. If you move from lower to higher potential, rise in drop. If you move from higher to lower potential, fall in drop. Then I1, I2, I3 are the three equations solve. We'll get expression for V0. How to find out the V0? V0 will be V0 minus I3 R3 minus V3 equal to 0. These are some problems which are related to the Kirchhoff's voltage law. These are like we have to calculate the E1, E2 and R. Find E1, E2 and R. Find the EMF of cells E1, E2 and the resistance R. Okay, well first we'll apply the KCL at this point. Here 3 ampere, here 5 ampere. Then it will be 3 ampere, 5 ampere. Then this should be 8 ampere plus minus, and this 8 ampere will enter here 2 ampere is approaching this junction from this particular point, from this side. 3 ampere will flow through this particular junction. Then how much of current should flow in this branch? In this branch it should be 1 ampere. And we'll apply again KCL at this point. If 8 ampere is entering here, 1 ampere leaving, then how much of current should flow in this branch? 7 ampere. Then here 2 ampere. Then here plus minus. Polarity we are going to give. First we'll calculate E1. Then applying the KVL, plus E1 minus 3 into 4 minus 3 into 8 equal to 0. So E1 minus 12 that's 6 volt. Then similarly plus C2 plus 8 into 3 plus 5 into 6 equal to 0. 8 equal to 24 minus 5 6 are 30. E2 equal to minus 4. Then we'll apply the loop equation for this. Plus E1 plus 2R plus E2 equal to 0. E1 36 minus 2R plus E2 will be minus 54. R equal to 54 minus 36 will be 18. 18 will be 9 ohm. This is a use of, so here we are applying the KCL, again at this branch KCL, again at this branch KCL, then applying the KVL. And this is one very fundamental things which are very important for exam. Next we have the effective, you have to find out the effective resistance RAB. Then first we have to, we are going to send the current I here. It will branch out I1 and I2. Next again this I2, it will branch out I3, I4, I5 and I6, and this is I6. So look at this I6. So these two same current flow, so these two are series. Then effective of that will be how much? 12 ohm. 12 ohm parallel to 6 ohm. Then replacing it will be like this. These two we have replaced. So what is the resistance of that will be? This will be 12 ohm. Now these two are parallel. Effective of this will be, again we have to replace it. Now look at this. The effective of these two will be 4 ohm. The effective of these two, 6 ohm and 12 ohm, they are parallel, so they'll become 4 ohm. Now how these two are? Again 4 ohm and 8 ohm, they are in the same current will flow, they are in series. So the next circuit will be, now how these two are in series. No, the effective will be 4 plus 8 will be 12. So here I am bringing that 12 ohm. Now 12 and 6 ohm, how they are? They are in parallel. These two are in parallel. So the effective of these two will be 6 ohm, 8 ohm, 4 ohm. Okay, this is 8 ohm, this is 8 ohm, and this is 4 ohm. these two we have replaced. Here. Now how these two are? So this will be again 8 ohm, 4 ohm, 8 ohm, 6 ohm, A, and this will be 6 and 12. The effective of this will be 4 ohm. The 4 ohm will be in parallel with this 4 ohm. Sorry, will be in series with this 4 ohm. So this will become 8 ohm. The next circuit will be, we have to keep on simplify like this. This is a basic idea. Eight ohm, 8 ohm, 4 ohm, 8 ohm, 6 ohm. This is A, this is B. Look at this 8 ohm, 8 ohm. They are in parallel. Effective will be 4 ohm. The next part of the circuit will be so how come you brought 4 ohm? So these two are how they are. They are parallel. The effective will become 4 ohm. Now 4 ohm and this 4 ohm, they are in series. So the next part of the circuit will be these two are in parallel. Effective will be 4 ohm. Eight ohm. So this is a method of series parallel. Okay, kids. Like if you have the circuit like this, what you should do is like you have to identify the series parallels. First, branch the current. Where the current remains same, they are in series. Where current branches, they are in parallel. Like this, everywhere the series parallel. Where current remains same, current branches. Current remains same, current branches. With that, you should identify and replace that with an equivalent resistance. So, what is the resistance across terminals A and B will be 8 ohm. So, we'll take the next question. Similarly, we have to calculate the current through all the branches. They are the base ideas based on the series parallel one. What is the resistance? This will be 12 ohm. So the effective resistance, this is 6 ohm. This is 12 ohm. This what is the resistance? This will be 12 ohm. These two are in series, no? Because the same current I1 will pass. Then this will be 12 ohm. We have to calculate those currents, and this what is applied voltage? 12 volt. Now here current will be I1, this will be I2. So how much I1 equal to? V equal to V by R, 12 by 12, 1 ampere. Similarly, same thing with I2, 1 ampere each. Then how much of current here will be? 2 ampere. The idea of these two are series, the effective is in parallel. Again, these three effective resistance will be in series. Next, we have the circuit. We have to calculate the current in all the branches. I1, here the total current here will be IT. It will branch here I1 and I2. Now this current again will branch here. Here we have the junction. So it will become I3 and I4. We have to calculate all these currents. So first we'll take the effective. 4 ohm, these two are parallel. Effective will be 2 ohm. 2 ohm, this will be again in series with this 2 ohm will be 4 ohm. And here effect will be 6 ohm. So one circuit will generate. This will be 2 volt, 2 ohm, 6 ohm, 2 ohm, 2 ohm, 4 ohm. This will be 10 volt. 2 ohm, so this will be 4 ohm. The effective of this will replace further. 6 4 ja, this will be 24 by 10, 2.4 ohm, 24 by 10 or 12 by 5. This is 2 ohm, 2 ohm, and this is 10 volt. I think we can calculate the total current. Or the total current will be 2 plus 2 plus 12 by 5 by 10. 32 by 50. 16 by 25. Now once we know that, so here how much of current? 16 by 25. Now we can calculate this I1 and I2 using current divider formula. I1 is equal to main branch current 16 by 25, other resistance by 6 plus 4. Similarly, we'll get I1 plus I2 equal to I. We'll get the value of I2. We know I and we'll get I1, we'll get I2. After getting I2, then we'll get I3 equal to I4 here. So therefore, I3 equal to I4 equal to I2 by 2. These are the simple ideas of series parallel. Very, very, very important. That's why I'm directly discussing some problems itself. Just will have the brief idea. These two are in series. Then effective that is in parallel. So this everything we can replace. Now similarly come for this one. These two are in series and that effective is in parallel. The total circuit will be the circuit we can show like this. R6, R4, 5. Here R2, 3, R1. So now these two are parallel, these two effective in series. So like this we should simplify. Now what about these two? These two are in parallel. These two are in parallel and that effective will be in series. Identifying series parallel is important. So if I go for current division, it will be like this. Here IA, IB, the same current R, here IC and IT. Now we have the circuit like this. We have to calculate the total resistance of this one. So let the EMF applied, let it be 10 volt. So how these two are? These two resistors, they are in series. These two are in parallel and that effective is in series with this one. First we'll replace the equivalent circuit. $80 ohm, 100 ohm, these two, 37 into 45. This will be effective of these two. It will be 20 ohm approximately, and this will be 75 ohm. I think now you can manage. These two are is how they are. They are in series. So the further effective circuit will be 100 ohm, 80 ohm, 95 ohm. Now again they are in parallel, replacing that with equivalent and solving. 100 into 95 by 195, 9500 by 195. Okay, fine. So like this we can calculate the current. Again, how these two are in series. There's a basic idea, series parallel. You should be very perfect in exam. Next one, we'll calculate this one. We have to calculate the effective resistance. Here the current will enter, will become I1 and this I2, and it will branch out. So how these two resistors, they are in series, that effective is in parallel. So the circuit will be 3 ohm, 1.5 ohm. Solve it here. Similarly, we have to calculate between points A and B. So current will enter here. Here I1, I2, and I3. These two are in series. These two are in series, and the effective is in parallel. So redrawing circuit, 5 ohm, 1 ohm, 5 ohm, RAB, 1 by RAB equal to 1 by 1 plus 1 by 5 plus 1 by 5. Identifying series parallel. Then, similar the next one we have here. We have to calculate the effective resistance across the terminals A and B. If you see the point C here, okay, A, B, this is a B, let this be point D. A and C are at, the one wire is there. So what to do with this wire? You have to short it up, make that common point. So we'll redraw the circle. This is a point D. This is C comma A, and this is B. Between D and CA, we have one resistor. Between D and A, we have another resistor. Between C and B, this is a resistor. So these two overlapping though will not get added to resistance. The effective resistance will become RAB will be 60 into 40 by 60 plus 40. 2400 by 100 will be 24 ohm only. These resistance will not get added up to the circuit. Very simple, very, very important. That's why I just brought this problem. So we take the next one. Equipotential. So we have the points X and Y. You see here a wire is there. Similarly, another wire is present here. Only one wire is there. So what to do with that wire? So make them as common pointer. So here, well, there's a point A, there's a point X, A and Y, they're common, and there's a point B. Between A and X, we have one resistor, R. Between X and Y, one resistor, that is R. Between Y and B, one resistor, this R. Between X and so we have to calculate the effective resistance. Y and X, Y and B, X and R, and X and Y. We have to calculate the effective resistance between these 2 points. So these two, how they are series, that effective is in parallel. So the next part of circuit will be R by 2. This X will be R. These two, how they are in series, 3R by 2. Solve it now. Now these two are parallel. Okay, we have this as some iron shaped rod is having some irregular shape. So we'll calculate this speed at this point, at this point, at this point. The speed at various points will analyze. So these are the some points I'm showing at point 1, 2, and 3. So the current I will flow like this. The same current because they are in parallel. So the current flowing will be same. Let me assume the structure like this. You can see clearly. Here I'm assuming one element. We are assuming elements like this. Now we have to just summarize what is the effective of what is the different area of cross section, what are the various conditions will come. First here, the same current I will pass through it. Same current I will flow through it. Area of cross section of this is A1, A2, and A3. Thickness let it be same. First, what is the resistance of these small elemental structures? We know like a dr1 equal to rho, thickness is same, but area of cross section, check it. From this generalized formula, A1 greater than A3 greater than A2. So therefore, what about the resistance? R1 less than R3 less than R2. Same current flows. Then what about the potential difference? The potential difference will be delta V1, because delta V1 equal to I R. So delta V1 less than delta V3 less than delta V2. What about the power dissipation in the element? Power dissipation should be equal to I square R1. So dP1 less than dP3 less than dP2. Okay, fine. There's a power dissipation. Then what about the disk speed? First we'll calculate the current density. Current density will be J1. Current density J equal to IA, area J1 less than J3 less than J2. Then the speed and current density are directly proportional. So VD3 less than VD2. So here the electrons will have less speed. Where they'll have more speed at this point? At this point, the electrons will have more speed than at this point, All power dissipation, resistance, potential difference, everything I discussed here. This based on what are the formulas we were using? Resistance equal this much, the current density is I by A, that this speed is given by eta into this one. That is, the current density is equal to concentration of electrons charge into this speed. So these are all the basic formulas already we have discussed. Based on that, I just summarized it, this conclusion. Okay, kids, now we'll take the next idea. The resistance of different shape conductors. If the cylindrical rod is there, then what is the resistance? Resistance is given by this particular formula. R equal to rho L by, where L is the length, area of cross section A, and the current I will be flowing normal to the area, this resistance. This is a tapered rod. Then what is the resistance of this? Given by R equal to resistivity rho, axial length L, and the area at the ends AB. So rho L by pi AB. This is the resistance of the tapered rod. Then similarly, the resistance of a thick shell. So how the current will flow here now radially outward. It will be current will flow radially outward. Then what about the resistance given by resistivity? Thickness of the shell B minus A, 4 pi AB. Now, these are the resistance of different shape conductors which you are supposed to remember. Next topic we have the open circuit. There's something. Open circuit. What do you mean by open circuit? Here at this particular point, you can see AB. This is called like a open circuit or some gap. What actually happens? Let's assume that a current I is flowing. Then positive terminal. We're assuming it. Then according to Ohm's law, I is equal to E by total resistance R by RAB. Or the resistance of the air gap will be infinity. E by R plus infinity. What is RAB? Because resistance of air, we are going to assume it several 100 mega ohm, so that will consider it to be infinity. Then this will become zero. No current flows. So across the open circuit, there won't be any flow of current. This is very, very important for us. Then what about the drop? Yes, there will be a potential drop. VA minus I into R plus C minus VB 0. Current 0, 0 into R, anything will be 0. What is the drop across this? Equal to E, applied EMF. Across open circuit, there won't be flow of current. This concept is very, very important. Now we'll take the short circuit concept. So this is a circuit we have. Now the current I will pass through it, plus, minus, plus, minus. So what is the I is equal to? The current through the circuit I is equal to E by total resistance of circuit R1 plus R2. Now we are going to close the switch. There is a wire. What conditions will arise, we'll see. Then these terminals will indicate AB. What is the resistance of the wire AB? 0. Very low resistance will approximate to be 0. Then any resistance in parallel with this, the effective will be 0 only. 0 ohm parallel with any other resistance, the effect will be 0 ohm only. So what we should replace here is short circuit only. So how much of current? Same I, and that current I will flow. So what is I is equal to E by R1. There will be flow of current. So actually what happens, this current I, it will not branch here. It will flow here. No current will pass through the resistor R. There won't be any current flowing through the resistor R2. The current, what happens, will take path like this. No current here. No electric current will pass through the resistor R2. So what is a short circuit? So this particular thing is what we'll call it as short circuit. So when a resistor is shorted, no current will pass through it. There's a basic condition. We have the now more than one loop, how to manage. So we'll assume here the loop currents. Let the loop current here I1. Any direction, sir, why you are choosing clockwise? You can choose clockwise or anti-clockwise. So the current here will enter positive, negative, here positive, negative, positive, negative, positive, negative, positive. So how you are giving polarity? Because the current should flow from higher to lower potential. So current is entering here, so this end should be higher, this should be lower potential. Similarly here, this current, this end, it is entering here, so positive, higher potential. It is leaving here, lower potential, negative. So plus minus like this will indicate. Then we have to write the loop equation. Traverse the loop. So we are going to traverse plus C1. I'll move from lower negative to positive terminal, rise in EMF. Then minus IR1. I1 R1. If you move from higher to lower potential, fall in drop. Minus C2. minus I1 R2 plus I2 R2 equal to 0. So there's a loop traverser plus C1 minus I1 R1 minus C2 minus I1 R2. You're moving from I to lower potential. With respect to this loop current, you're moving from low to higher potential, rise in drop, rise in drop plus I2 R2 equal to 0. Similarly, we'll traverse the loop like this. So can you indicate the direction of traverse? Yes, we have indicated. Now I'll traverse the loop like this. Any direction, any direction you can traverse it. Then this will be plus C2 minus I2 R4 plus C3 minus I2 R3 minus I2 R2 plus I1 R2 equal to 0. Look at this one. Plus C2 minus I2 R4 plus C3 minus I2 R3 minus I2 R2 plus I1 R2. How many unknowns are there? I1, I2, two equations, two unknown solving, we'll get the difference. This is a basic idea of the loop method. If three loops are there, I assume three currents, three loop currents. If four loops are there, four loop currents. Next, we'll start the nodal analysis. Here, instead of that loop current, we'll go for the nodal analysis. Here, we'll define the potential. Let it be V. V naught, I'll write it. Potential of let this be 0, 0. Potential here will become E1. Potential here, let it be E2. There's one more method I brought it. There's everything is zero potential one. So now you define, this is one basic idea. Across a cell, what is the potential difference? Plus C2. Potential difference across cell is E2, no? So let this be 0, let this be E2. Similarly, potential difference across cell is E1 and 0. This will be V0 and 0. So this everything is zero potential. Then here, nothing but we are applying we don't know like current, which current is entering leaving. So altogether, the algebraic sum of current entering a junction should be 0. So therefore here, V0 minus E1 by R1, V0 minus E2 by R2, V0 minus 0 by R3 equal to 0. Solve for V0, we'll get the required answer. So how you are writing? This particular Ohm's law we are applying across this. So let's assume that what is the direction of current? We don't know. We are assuming that current will flow like this. So V0 minus E1 by R1, V0 minus E2 by R2, V0 minus 0 by R3. I'll solve, I'll get the V0, I'll substitute here, then I'll get the current in individual branches. This will be much easier, no? There it was two unknown, here only one unknown, we'll get the answer. We'll take the next one. Same nodal analysis, based on the nodal analysis. No, this will be how to assume the things. Here I'll start from here. Let this be 0, 0 potential, 0 potential. There's a one common wire, so 0 potential. So this one will be 10 volt. This will be 4 plus x, and this will be x. Because what should be the potential difference here? The potential difference should be could 4 out, no? 4 plus x minus x will be 4. So we'll write down the loop equation for this particular circuit. what about the current equations? How to generate current equations? So there will be a, we'll take this junction. I'll indicate like this. We'll take the junction G. Or anything you can write it. Any of the junction you can pick it up. We are defining, so we'll do one thing. This is like a, we'll assume some V1, some value will assume, or A will assume it. The potential difference, let it be B. Then let the current here be I1, I2, I3, let this be I4. So this is the called a super node. Just for learning purpose, I brought this one. So look at this particular cell. The total current entering here I1 and I4, and how much of current leaving I2 and I3. So for this, we'll write down the equation. I1 plus I4 equal to I2 plus I3. What is I1? 10 minus A by 2. What is I4? I4 will be 10 minus B by 1. What about I2? I2 will be A minus 0 by 6. I3 will be B minus 0 by 4. A and B are unknown, so we'll write one more equation. A minus 4 minus B equal to 0. So A minus B equal to 4. Two equations, two unknown. So these are some problems related to nodal analysis. Next we are going to discuss internal resistance of a cell and grouping of cells concept. So the charge here will assume will flow like this. The cell there's a resistance here. There's a resistor R there. There's a cell. It will send out the charge. There's a cell. Duracell. Everyone. No. Positive charge will come here. Positive charge will enter here. Positive, negative. And the current I will flow in the direction of it. And the same positive charge will enter here. This positive charge, why did it flow means because of the electrostatic force that is generated by the cell. So the electrostatic force will be acting like this. Then this charge will encounter collisions, and because of this it will experience a resistive force by the material. Here, this is small, very beautiful concept. Try to understand. What makes the charge to flow? This is a lower potential. This is a higher potential. So there's everything. We are drawing an equivalent circuit like this. E, and this is R. This is a terminal A, and this is B. And here current I is flowing. Okay, with this. So inside this cell we are discussing. the charge, what is VAB? VAB equal to E. So VA greater than VB. So, but the charge open, the positive charge has to move from lower to higher potential. So for that purpose, the cell has to do work. At the same time, when the charge is flowing, the material of the cell, the material of the cell, the material of the cell, what it does, it will offer a resistance to the flow of charge. And this resistance by the material to the flow of charge, what we can call internal resistance. So where we have to show that internal resistance, the internal resistance has to be shown like this. What is this R? By this material. What is that material? The chemical which is present inside the dry cell that will offer the resistance to the flow of charge. So that is what we'll call internal resistance. And these particular points are called as the terminals. These are the terminals, A and B. A and B, they are called as terminals. Now, what is the expression for I? I is equal to E by R plus R. Terminal voltage will calculate. VA minus E plus IR minus VB equal to 0. So VAB is equal to E minus IR. So what is the terminal voltage? Will be less than applied EMF. This is a formula. So what all power generated, a part of that will be dissipated across this resistor, remaining will be across the cell itself. So like this we'll define the efficiency of a cell. How you define efficiency? Useful output power by total power or total input power. What is the useful output? Will be I square R. What is the total input power generated? That will be E into I. Will be IR by like this. So what is further I is equal to? I is equal to E by R plus R. So the efficiency of a cell depends upon these things. If the internal resistance is 0, then efficiency will be 100%. If internal resistance is more, then efficiency what happens will decrease. So therefore, what should be the internal resistance of cell? Should be as less as possible. If internal resistance is 0 here, then the terminal voltage will be applied EMF. So internal resistance of cells should be as low as possible. This is a basic idea of a cell. Now we'll take the grouping of cells. If the cells are connected in series, I think you might have come across, you know this one. Cells will connect in series like this. Same current I will flow. Then what is the expression for current I? Expression for current I is equal to NE by R plus NR. Okay, this is the expression for this current I. Then if you want that drop, V equal to IR. This external resistance what you have calculated, this drop is equal to IR. So this will become NER by R plus NR. This is a drop across resistor. Similarly, if they are in parallel, if the cells are connected in parallel, grouping of cells, if they are parallel, then the current here I1, I2, I3, like this IN. The total current will be sum of I1 plus I2 plus I3 and so on. What is I1 will be E minus IR minus I1R equals 0. So I1 is equal to E minus IR by R. We'll substitute all the values. all currents will be same, Ni it will become, and then anyway I can substitute here, and so on. What is the total? This will be Ne IR Ne by small r. So I is equal to Ne by R plus Nr, or E by R plus Nr. Okay, this is the expression for the current through the external resistor R. If their cells are in parallel, now we'll go for mixed grouping of cells. Directly I'll write down the formula. So we have to calculate the expression for this current I. Summation of EMF should be equal to summation of E by summation of R. Now the EMF, the effective EMF will be summation of E by R. This will become E1 by R1, E2 by R2, E3 by R3, En by 1 by summation of R equivalent. R equivalent will be 1 by R equivalent. And this is symbol like this. E equivalent, R equivalent. Summation of 1 by R. 1 by R1, 1 by R2. One by Rn. So what is the expression for I? I is equal to E equivalent by R equivalent. E1 by R1, E2 by R2. By R3 and so on. You have to remember this formula, sir. E equivalent and R equivalent. We take the next bulbs in series parallel. These are the two bulbs are there. Okay. Okay, this is a cell which will supply the energy, and this is a bulb which will have the power rating and also the voltage rating. Then directly we'll take the problem. So this power rating of the bulb, it is say 10 watt, and the voltage rating is say like a 200 volt. Then what is the power rating? There's a maximum power it can dissipate, and when you say voltage rating 200 volt, there's a maximum voltage which it can withstand here. With this, what happens? We can calculate the resistance. Pm equal to Vm square by R. Then we'll get the resistance of the bulb. So what is the power rating? 10 watt. We'll make it 100 watt. Then voltage rating 200 by whole square by R. So R equal to 40,000 by 100 will be 400 ohm. Okay, now if I connect this particular bulb across a cell whose EMF is more than 200, it will burn out. Now, this concept is very important. Rest all you can manage very easily with the first situation. So I'll bring the EMF, which is say like a 210 volt. Then what will happen to this bulb? Bulb will get damaged. Damage means will burn out. Why? Because here applied EMF V greater than Vm. Bulb will not be safe or burns out. Will not be safe. Then if you apply the voltage which is less than that one, say like a 190 volt, is bulb will be safe. Then how to calculate how much of power it will dissipate? How much of power dissipated will be applied EMF E square by R. E square is how much? 190 square by R is how much? 400. This power dissipation you calculate will be less than maximum power dissipated. What is the idea of this one? The bulb will be safer. When bulb will be safe, when applied voltage across the bulb is less than the voltage rating, it will be safe. And the power dissipated will be less than the power rating. When the applied voltage across the bulb, if it is greater than the voltage rating, the bulb will burn out. There's a basic concept. Okay, now such a bulbs, if they are connected in series, then what is it? So like here, this having the voltage rating, this having the V. These are the bulbs. So this having the resistance R1, R2, and R3. Then the same current I will flow. Then what is the power dissipated across first bulb, second bulb P2, third bulb P3? P1 equal to I square R1, P2 equal to I square R2, P3 equal to I square R3. And if I give condition R1 greater than R2 greater than R3, tell me like which bulb now will have more brightness. So based on this, P1 greater than P2 greater than P3. So bulb brightness of the bulb 1 will be more than that of 2, that of 3. These are the brightness comparison. So when bulbs are in series, so we will compare the brightness by using the power dissipation. Since same current flows, the one which is having higher resistance will have more brightness. So what is the conclusion? What is the conclusion will make it? Bulbs of higher resistance will glow with more brightness for series, for series. And this is a concept. Yeah, similarly, bulbs in parallel. let they have the resistance R1. Resistance of this bulb be R1, R2, and R3. We have applied the potential V. All are having same potential. Then whatever the power dissipated, now we'll put a condition R1 greater than R2 greater than R3. The resistance of this bulb is greater than this, then this. Then whatever the power dissipation P1 equal to same drop, no? So R1 greater than R2. So P1 less than P2 less than P3. More brighter. So bulbs in parallel, lower resistance bulb will have more brightness. And this is a concept. Next we have the Wheatstone network. The potential when the current through galvanometer will be 0. So in fact here current will flow like this. I, this will be IA, IB. The current here, it will not branch, it will remain same. So this will become IA. Here also the current here will not branch. So the same current will flow, and this is the I. So what is the current through the galvanometer? It is 0. Current through galvanometer 0 means VD minus IG into G minus VB 0. If current through galvanometer 0 means VD equal to VB. So even if any resistors are there, you can remove that since there is no resistance. Then out of this total circuit, it will appear simple series parallel. R3, R2, R4. When when this condition arises, then R1, R3 by R4 equal to R1 by R2. There is a condition for balance. We can say the bridge is balanced and current through galvanometer is 0, and any resistor connected here, it can be removed here. So these are basic ideas of the Wheatstone network. Then there will appear simple series parallel. The current will flow here, the current will flow here. All these are examples of Wheatstone network. If the condition, when you can remove this galvanometer, you can remove this galvanometer if ratio of these two arms, P by Q, if it is equal to R by S, then we can remove the particular galvanometer. P, Q, galvanometer, RS. The same Wheatstone network, only it is just connected in different way. Then what is the condition? P by Q. If this condition satisfies, we can remove this circuit. We can remove that galvanometer. Okay, with this, like this, we will be having the P by Q equal to R by S. All these are the conditions of Wheatstone network. Next, we have the circuit's equivalent resistance network. Now, these are the current I will come. It will branch out like this: I1, I2, I3. We'll assume like this. This current is I1. This I1. Let this be I2. Here I3. Here I3 will combine. Similarly, the current here will be I3, I4, will be I2, so it will be I1, and this will be I1. I2, okay, this is I1, I1. Now this will be same thing. So how much of current enters? I1, I2, I1. Here say I2, I1, I1. The current will not branch here. The current will not branch here. The reason for that, because we have the symmetry here. If you see, the current is distributed symmetrically about this vertical line. Symmetric line. So therefore, the current will not branch here. If the symmetric line passes through a point junction, And if the junction what happen will just be physical, will not be electrical. So now we have removed it. Then now these two are series effective in parallel. Then the circuit will appear like this. R R by 2 R R R. R. Then we can simplify series parallel. Next again, I just solved it. The current distribution, we have to calculate the effective resistance RAC about these 2 points. Here the current I will come. It will branch like this, I1, I1, here I2, I2 by 2, I2 by 2, I2 by 2, I2 by 2, and it will combine I2, and this will be I1, and this will be I1. No current will flow through these branches. So remove them. Once you remove, so we'll get these two are in series, these two are in series. Next, these two are in series, these two are in series, and these two are in parallel, and that effective will be in series. Solving like this. Okay, agreed. These are the some ideas which I'm sharing. Equivalent resistance. Then total will be 3R by 4. We take the next one. This is about the cube. We have to calculate the effective resistance across A and B. So where is A? A is here, and B is here. We have to calculate effective resistance. The current here, how do it will symbols gone wrong. Effective resistance RAB it should be. Let me do one thing. I'm missing symbol AB. It is. This is D. This is C. This is C. This is C. Fine. This is DM. This is a circuit. We have to calculate the across the diagonally opposite points across A and B. Then if you see the circuit condition, this C and this D. So let me indicate that is the points. So when I send the current I, 3I, it will branch here I, and this will be I, and this will be I. It will further branch here I by 2, I by 2. This current I will branch it as I by 2 and I by 2. This will combine I by 2, I by 2. This will be I. Total will be 3I. Then if you see the potential, said potential of these points will be same. So we are making them as equipotential, joining them between A and C one resistor. These resistors will bring like this. Then DB resistors, they are connected here. Between C and D, we are connecting 6 resistors. Then this circuit will be further. This will be R by 3, R by 6, R by 3. We'll calculate. So we'll get the effective resistance. No. We have to calculate the effective resistance between points A and B. From here, let the current enter. Here I1. Let R be the resistance of all the circuits. Current will not branch I1 and I1. These are the points 1 and 2 will write it. Further, the current will not branch I1 and I1. Current will not branch here. This will be I1. The current will not flow here, will not flow here, will not flow here. The reason for that, potential V1 equal to V2. Similarly, these points V3 equal to V4. Similarly, these points V5 equal to V6. So then the effective resistance this is the point A, B, 1, 3, 5. These are R, and R. Okay, all these resistors they are in series. They are in series. The effective they'll be in parallel. So the next part of circuit will be R. This will be 4R. This will be 4R. Okay, now we can calculate. Next topic we have the conversion of galvanometer into ammeter. The first one. Next part, conversion of galvanometer into ammeter. There's a galvanometer. It can maximum current, it will read Ig. So we have to convert this into ammeter. So what is ammeter now? Galvanometer connected a resistance in parallel with this. This is called like a shunt. Low resistance in parallel. This will indicate by symbol S. Then these two are parallel. So Ig into G is equal to I minus Ig into S. So what is the shunt is equal to? Ig into G by I minus Ig. This is the current, maximum current to be measured. We also call that as I max. This is also called as I max. So as the range increases, galvanometer range increases, the shunt value will decrease. There is one formula which you have to remember for to convert the galvanometer into ammeter. You have to connect low resistance in parallel. Then what is the resistance of that will be given by this particular formula. Similarly, we take the conversion of voltmeter, galvanometer into voltmeter. Then this will be V is equal to a current Ig will flow. There is a galvanometer. Then this should be equal to Ig into G plus Ig into Rs. Applying the KVL. So the range depends upon V minus Ig into G by Ig. So as the range increases, this particular range increases, the resistance connected in series with the galvanometer, its value also will increase. I resistance connected in series. So over the voltmeter resistance will be Rs plus G. What about the emitter resistance? I forgot. The emitter resistance will be Ra will be Gs by G plus S. We'll take the next concept. There's a meter bridge. Why do we are meter bridge? It contains a meter scale here. Okay, everyone. I think you are looking at this scale. We have meter scale. These are the connectors. These are connectors, metal strips. The known resistance, it is connected here. The known resistance, and there's a galvanometer connected here, and there's a cell. We have the keys. So there's a circuit here now. So the unknown resistance, the R, R is a known resistance. S is a known thing. This I'll indicate here. You can see the S is here. Then it works on the principle of Wishtone network only. So first what I do, there's an electrical connection. You have to look at this particular electrical connection. There's a cell, E or V, both are same. From positive terminal, we are connecting to this particular pointer to R and the length L1. From positive terminal to the length L1. Okay, there's a length L1. L1 I'll indicate. This is 100 minus L1. Current will flow like this. Cell, current. Okay, it is connected to the resistor AB. And next this is BC. Symbols also a little bit. Okay, we'll do one thing. AD. DC. B is this one. There's a point A, B, D, and this is C. Okay, there's a, like this we are having, there's a known resistance in this gap. This is called like a left gap. This is called like a right gap. So we have connected here. Now first, like when this is called like a jockey. This particular thing is called as a jockey. A mobile sliding rod it is. There's the only thing. So it can be, I can slide it here. Then, when the bridge is balanced, when the galvanometer shows deflection, zero deflection, then I'll note down the length L1, and that will add up. This will be a galvanometer wire. The thick one, well, I'll show the galvanometer wire. This is a galvanometer wire. These things will confuse you. I'll remove them. It will be easy for you. So this will be the length, balancing length is L1. There's a scalar, there's a galvanometer wire or the potentiometer wire, what we'll call, which will have length equal to 1 meter. So 1 meter means 100 centimeter. So here this length AD will add up some resistance. How much it is? L1 length will add up resistance. Then the remaining DC length of the wire will add up a resistance that we are showing it here now. RDC we can call it. Okay, now when the current through galvanometer is 0. When current through galvanometer is 0, then what we can write here, RAB by RBC is equal to RAD by RDC. What is RAB? R, and this is S. This will be lambda into resistance L1. This will lambda into 100 minus L1. Then we'll get R by S, the unknown resistance S needed. S is unknown thing. The known resistance S will be R into 100 minus L1 by L1. I know L1. L1, we know it. I'll get the resistance S. Then once I know the resistance S, then I'll calculate the rho. I'll measure the length L naught and area of cross section pi r square. I know the resistance S. I know the length of this wire L. It is indicated here. L it is indicated. I know the radius of this wire also, unknown resistance. I'll get the resistivity. Resistivity will be given by S phi r square by L. Like this, we can find out the resistivity of that particular material. There's a basic idea of the meter bridge. It works on the Wheatstone network. Now in the meter bridge, we are having this end correction. This galvanometer wire. No. Some length of the wire will be used for the connection, and this will what happen, we are unable to measure it. It will also add up some resistance. So these are called as end correction because a part of wire is used to make the connection, and that particular resistance also should be considered. For that purpose, we are bringing the end correction, and the current through galvanometer will be 0. The strict condition, current through galvanometer will be 0. This will be 100 minus L1. Current through galvanometer is 0. Then here R by S is equal to lambda L1 plus alpha equal to lambda 100 minus L1 plus beta. R by S is equal to L1 plus alpha 100 minus L1 plus beta. Alpha and beta are the lengths which are used for lengths of wire used for connection and cannot be measured, only can be determined, and that's what we are doing. Similarly, current through the galvanometer will be 0. Then S by R equal to lambda into L2. What is the resistance of this will be? This length L2 plus alpha will be added. No? So therefore this will become plus alpha is equal to 100 minus L2 minus beta. Here minus beta I was missing. Okay, dividing this S by R is equal to. Okay, solving alpha and beta. Two equations, two unknowns, solve for that. So like this we can determine the end corrections. Next we have the potentiometer. It's a device used to measure the EMF and internal resistance of a cell. Okay, now I'll what all it will have? This is called like a potentiometer wire AB. This is called like a standard cell. This part is called as a primary circuit, and this is called like a secondary circuit. first we have to measure the EMF and internal resistance. So for that purpose, okay, this is a standard cell. Or the primary circuit. This will be secondary circuit. Now let's do one thing. Here the current through galvanometer is 0. The current through galvanometer is 0. So therefore the current will not branch here, will flow like this. The current will flow like this. The current will come here, will flow like this, and current through galvanometer will be 0 when the bridge is balanced. Then the drop VAY should be equal to EK because there is no current through the galvanometer. What is VAY? VAY should be equal to current I lambda L1. Similarly, we'll connect another cell, this one in the secondary. And the primary circuit, as usual, the standard cell will be there. Same current will flow here. And the current through galvanometer will be 0. And the current through galvanometer will be 0. Then the drop VAY1, new length, this will be VAY1, VA dash, I'll write it. VAY dash should be equal to I into lambda L2. Current into the resistance of this wire, lambda into L2. This should be equal to, what this should be equal to? Unknown resistance EU. Because there is no current to the galvanometer, so therefore this drop should be equal to VAY2. So this should become equal to I lambda L2 equal to EU. So ratio of this EU equal to EK by L2 by L1. Like this, we can calculate the unknown EMF. Then how to get the resistance? Now the same primary circuit, there's a primary circuit, the same cell is there. And there's a secondary circuit, the unknown EMF is connected. And one resistance, external resistance also will be connected. Here, Y double dash like this. And the same current I will flow. Current through galvanometer will be 0, but there will be a flow of current here. And no current here. And no current will flow here, but there will be flow of current. There will be flow of current here. And as usual, this current I will flow. This current I will not branch because current through galvanometer is 0, so will not branch I. So now VAY dash is equal to this X and C and D, I'll write it, equal to VCD. VAY dash equal to I lambda L3. What is VC dash? VC minus EU What is I is equal to? I equal to EU by R plus RU. So I'll substitute this one. EU R by, we have to calculate the, so already we know I lambda L3, I lambda, this is unknown, this equation will, we have to calculate RU, that one, from previous data. What is EU unknown is equal to I lambda L2. We'll write it here. Dividing these two equations previously. So this will become EU R by R plus RU O divided by EU is equal to I lambda L3 by I lambda L2. We have to calculate this RU. So EU also get cancels. Then this will become R plus this is unknown resistance. So what is R? R is the resistance box. This one. You have to remember I derived it. You're supposed to remember this one. So just by, if you know, we know capital R, we know L2, L3, we'll get this unknown resistance. This very difficult to measure internal resistance of cell, we are able to calculate. So what is RU? Internal resistance of a cell. Next we have the, we know that as we increase the temperature, the resistance of that will increase. Why do it will increase means, as we increase the temperature, the atom starts vibrating about mean position, their amplitude and frequency will increase. Due to that, more number of collisions will occur, and hence the electron passing through it will encounter more collisions, the resistance will increase. So therefore, as we increase the temperature, the resistance of conductor will increase. Therefore, the graph. This is everything, we are writing it mathematically by this particular formula. So what is the basic formula for R? R equal to R naught 1 plus alpha temperature, T minus T naught. So this is a resistance of the temperature, where alpha is called as a temperature quotient of resistance for conducting material. R naught is reference. T naught is a reference temperature. T is the temperature of the conductor at any degree Celsius. And what is capital R? Resistance of conductor at time t. So like this we define the the resistance of a conductor, which will vary with temperature. When such two resistors they are connected in series, then what is the effective alpha of that will be? This having alpha 1, temperature quotient of resistance, this alpha 1, of this is alpha 2. What is the effective alpha? Given by this particular formula. What is effective R? R will be same thing. R equal to R naught equal to R naught 1 plus R naught 2. Similarly, R equal to R1 plus R2. When they are connected in parallel. When two resistors are connected in parallel, the effective resistance R naught is given by this particular formula. Effective temperature coefficient of resistance. So here it is having alpha 1, alpha 2. Effective temperature coefficient of resistance will be alpha 1 R naught 2 plus alpha 2 R naught 1, R naught 1 plus R naught 2. This is a basic formula. Okay, fine. Like this, we'll get the thing. Okay, this is a basic condition. Okay, kids, like we had the discussion about the uh, current density one shot. In briefly, in 2 hours, I revived. It's a very lengthy chapter. Almost all ideas I covered it. Once I rewatch it, learn, remember all the formulas, then go for the solving PYQ. Okay, all the best. Do prepare well for the April session. Thank you everyone for great support. Thank you.